Discuss this theorem. So in this theorem, we have to prove that a differentiable function is continuous. Already we have proved this thing for a function from R to R. But right now we have a scalar field and we have to prove that if it is differentiable at A, then it is continuous at A. Let us write the given thing. We have f is differentiable at A belongs to S. And what we have to prove that f is continuous at A belongs to S. So using epsilon delta definition, we are going to prove it. So for that, we need to have one epsilon first. Let us take epsilon. Let epsilon greater than 0 be given. Okay, so we will start with the given thing. The given thing is f is differentiable at A. We have f is differentiable at A belongs to S. Simply, I am going to use the definition. You remember the definition? So the definition says if f is differentiable at A, then there exists a linear transformation T. Okay, I will write that thing. So therefore, there exists a linear transformation T from Rn to R such that for given epsilon greater than 0, there exists delta greater than 0. But see, epsilon already we have taken, so I will write for above epsilon greater than 0. For, just a minute, let me rectify. For above epsilon greater than 0, there exists delta greater than 0 such that norm h less than delta implies mod f of a plus h minus f of a minus t of h divided by norm h less than epsilon. Using definition, we could write it. But see, one adjustment I am going to do, that is instead of epsilon, I am going to take epsilon by 2. So in next step, what will I do? I am going to shift this norm h on that side. Then see what will happen. Implies mod f of a plus h minus f of a minus t of h less than, getting epsilon by 2 into this norm h. Epsilon by 2 norm h. This is statement number 1. Okay, so one information we have. See, here we have got a linear transformation. We know that every linear transformation is continuous. So let us use that thing. We have T is linear transformation. So that's why T is continuous at A. So this is linear transformation. That's why we can say it is continuous at A. So we can use the definition of continuity. Therefore, again, for given above epsilon greater than 0, therefore, for above epsilon greater than 0, there exists delta greater than 0. But see, already we have taken delta. So what will I do? I will call it as delta 1 and I will call it as delta 2. So this is my delta 1 and this is my delta 2 such that norm h less than delta 2 implies mod t of a plus h minus t of a less than epsilon. Again, adjustment I am going to do. Instead of epsilon, I will write epsilon by 2. But see, T is a linear transformation. So you know the property of linear transformation, f of x plus y is equal to f of x plus f of y. That means you can take separate addition. So same thing I can do here. T of a plus h, that means t of a plus t of h. Let us do that. So implies mod t of a plus t of h minus t of a less than epsilon by 2. Can you tell me the next step? Obviously, t of a and t of a will get cancelled to each other. So therefore, we will have mod t of h less than epsilon by 2. This is statement number 2. A very important thing we have got here. Okay, but see, the problem is statement number 1 is true for norm h less than delta 1 and statement number 2 is true for norm h less than delta 2. So I will choose minimum of delta 1 and delta 2. So both of them will be true simultaneously. Let us do it, but there is no more space to write, so make a screenshot of it, then we will go further. So I have selected here minimum of delta 1 and delta 2. Okay, so see, we have called it as delta. So 1 and 2 will be true simultaneously for this delta. So let us come back to the last point, that is we have to prove that f is continuous at a. So let us do that. So for that purpose I am going to consider norm h less than delta implies mod f of a plus h minus f of a. See, we have to prove this is less than epsilon, then we can say yes, f is continuous at a. Let us try to do small adjustment. I'm going to do, that means minus t of h and plus t of h. I'm going to add and subtract t of h. So let us see what will happen. So this is equal to mod f of a plus h minus f of a minus t of h plus t of h. So you know that if I take separate mod, value will get increased. So therefore this is less than or equal to mod f of a plus h minus f of a minus t of h plus mod t of h. Okay, but see, statement number 1 says this is less than epsilon by 2 norm h. Statement number 2 says this is less than epsilon by 2. See, I will say from 1 and 2. But see, one thing already we have mentioned here, that is norm h is less than delta. So this is less than epsilon by 2 into delta plus epsilon by 2, since norm h is less than delta. See, what will I do? We have selected delta is equal to minimum of delta 1 and delta 2. I will take 1 also. So that's why what will happen, see what will happen, I will show you here. This is less than or equal to epsilon by 2 into delta is minimum of delta 1, delta 2 and 1. That means delta is less than or equal to 1. So that's why I could write this is delta is less than or equal to 1 plus epsilon by 2. So this is epsilon by 2 plus epsilon by 2, which is epsilon. So that means finally we proved, yes, mod f of a plus h minus f of a less than epsilon. So therefore f is continuous at a. So therefore f is continuous at a. So in this way we proved. So therefore we proved every differentiable function is continuous. Okay, make a screenshot of it. After that we will stop. Thank you. Bye bye.